All right, clip number 2 in section 3 notes on areas of polygons. In the previous clip, we talked about quadrilaterals, a couple of very unique quadrilaterals, namely a rhombus and a kite, but still in those early introductory simple polygon shapes. Triangles will still be 1/2 base times height. Quadrilaterals will still be generally length times width, with the exception of those two unique shapes that we had in the last clip, a rhombus and a kite, where it was each diagonal length multiplied by each other and then cutting that value in half, and that's the area of a rhombus or a kite. In this clip, we're now going to expand our area understanding to beyond just the simple 3-sided shapes and 4-sided shapes. Namely, here in this what you see on screen right now, in the margin right here, this is a 5-sided pentagon, and over here this is a 6-sided hexagon. Now these are just the next 2 levels up in number of sides of shapes. The good news here, and I'm going to introduce it a little bit later in this clip, the formula that we're going to end up using for finding the area of any polygon is going to, one of the variables is just counting the number of sides of the shape. Whether you're shown the diagram, you're literally just counting the sides, or you are explicitly told, here's the name of the polygon we're finding the area of, and then we just pull the number out of that name. Okay? So before I get into that, though, there is going to be one kind of important piece of understanding here. We're going to be dealing with regular polygons. That term regular is a term that we have come across before in a previous unit. And there is a lot of baggage that comes with that term regular, even though it's quite literally just a regular word. Okay, when we talk about a regular polygon, whether that's a simple triangle or something complicated like a 10-sided decagon, a regular polygon has a few key attributes. Number 1, and that's this first bullet point right here, it's equilateral. A regular triangle means that's an equilateral triangle. All 3 sides are congruent to each other. A regular quadrilateral would be a square. And it would have to be just a square, and that's going to get to the second part of the definition in a minute, but I'll come back to that one. But like a regular pentagon, all 5 side lengths would have to be the same length. Regular hexagon, all 6 side lengths would have to be the same side length, and so on and so forth. The more complicated the polygon, again, a regular polygon, each of the sides has to be congruent to the other. Tied to it, and I didn't write it here, but what's also tied to this equilateral aspect is that it has to be equiangular. Okay, and that term right there, that $5 word with all the vowels in it, equiangular means that each of the angles, the interior angles of the shape, must also be congruent to each other. So, for instance, a regular triangle would not only have all 3 sides congruent to each other, but each of the 3 angles would be forced to be congruent to each other as well. In a regular quadrilateral, if I were to just say equilateral, a rhombus is technically an equilateral quadrilateral. All 4 sides are congruent to each other, but it's not regular because all 4 angles would have to be congruent to each other. And the only way that happens is if I have a square, where all 4 angles would be 90 degrees. For a pentagon, all 5 of these angles would be congruent to each other. For a hexagon, all 6 of these angles would be congruent to each other, so on and so forth. Okay, but now let me get into a couple of other features that are also true that we didn't discuss before. And there are these other bullet points. So this equilateral, equiangular type of feature kind of dictates the shape. We're going to get these nice kind of what we would call like toddler block type of shapes, like what you would see like in a toddler's block set that they stuff into those holes and stuff, right? Okay, so these other bullet points would be like this one. The distance from the center of each of these regular polygons to each of the vertices or corners, however many there may be, the distance from the center to each of the corners has to be congruent as well. So the number of corners is completely determined by the number of sides. So in a triangle, there are 3 corners, quadrilateral 4, pentagon 5, hexagon 6, so on and so forth. Okay. The distance from the center of this figure, so for instance right here in this hexagon, the center of this hexagon at point P, the same distance it is from P to M as it is to P to N or anywhere around in these 6 corners. You'll notice that I labeled it R, and that's on purpose. We're calling that the radius of this polygon. Because by definition, and that's kind of the reason why it's piggybacked on chapter 10, which was on circles, why it was piggybacked here from in this chapter that deals with circumference, area, and volume, that deals a lot with circles, is because you'll notice that I drew a circle around each of these shapes. Because by definition, a circle, the distance from the center of that circle to the outer edge is the same distance everywhere. And so if I'm talking about that with a polygon, even though they're corners, it would be what we call inscribed inside of a circle. Another term we've come across before in recent units. And so the distance from the center to one of the corners would be the same as the distance to the outer edge of the circle, which we would define as radius. That only is true in regular polygons. As soon as I have irregularities, like it's just kind of a warped type of shape, it doesn't follow those rules anymore, and so then there was kind of variations involved. So when we're talking about the family of regular polygons, this is going to be true. The distance from the center of whatever polygon I'm talking about to one of its corners has to be the same everywhere. And then this is a brand new term altogether. Apothem. Apothem. Apothem is the distance from the center to each side of a polygon. And that's a subtle difference. It's actually a slightly longer distance to go from the center of this hexagon to one of the corners than it is to go from the center to one of the sides. Okay? The distance from the center to one of the sides has to be what we call a perpendicular distance. That's why you see this little perpendicular box right there. Same thing goes over here. The apothem distance, or the distance from the center to the side, is perpendicular to that side. And that's a slightly shorter distance than out here to the circle. That's why if I were to see the circle, the curve right here, the side of this pentagon is obviously a little bit closer to the center than it is at the circle there. Same thing with the hexagon. The distance to this Q point, the apothem distance, it's a little bit closer than to get to all the way to the edge of the circle, because that's what will distinguish a circle from this hexagon. But we call that distance apothem. That ends up being a critical measurement for finding the area of any polygon. So we'll come back to that one. And one last little key fact here is this: central angles. When I talk about a central angle to a polygon, whether we're talking about this pentagon, this five-sided pentagon over here in the margin, or this hexagon right here, I can fundamentally split these up into triangular slices. Okay, so in this hexagon, I create this triangle by both of these radii distances, the distance from the center to each of the corners, and then the third side being one of the 6 sides of this hexagon, I create this triangle slice. This triangle slice will be the same congruent slice as each of the other 5 slices in this hexagon. Okay, 6 slices in total. And then this triangle slice here in the pentagon, there's going to be 5 congruent triangle slices in this guy. Okay, it depends on the number of sides. Well, the central angle would be the measurement of this wedge piece in the middle, which is going to be the same as each of the other slices in this hexagon. But the central angle right here can be measured by this: 360 degrees to complete a full rotation around this interior, divided by the number of slices there would be. In this hexagon, there'd be 6. So this central angle here would be 60 degrees, 360 degrees divided by 6 sides. In a pentagon, I would take 360 degrees divided by 5 sides. That would tell me the central angle measurement of this little wedge right here, which would end up being 72 degrees. And it kind of changes from polygons after that. But it can be measured by simply taking 360 degrees, dividing by the number of sides. That will be the central angle wedge here. That will also become important when it comes to measuring other aspects in that triangle slice. Okay, so it's actually worth pointing out here, one of the critical, again, measurements here is this term apothem. The distance from the center of this shape to one of its sides. Again, notice it makes a right angle. That's important here because this apothem is going to split this slice directly in half. This triangle slice that makes up 1/6 of this hexagon, 1/5 of this pentagon. The apothem, in whatever case, in whatever polygon I'm dealing with, splits it directly in half. So for instance, with the central angle, if I knew that this 60-degree central angle existed because it's a regular hexagon, this apothem splits it into two 30-degree measurements for each of those slices. Here in this pentagon, the 72-degree wedge slice there, the apothem splits it directly in half, creating two 36 degrees split right there. That ends up becoming very important because now I can start figuring out measurements for lengths of sides, because I want to point this out before I move on. The fact that that's perpendicular, the apothem is perpendicular, I've created two right triangles, two congruent right triangles, no less. And that's important because now that I have right triangles, there's a lot of baggage that comes along with the right triangle as well. As soon as I have a right triangle, I can now use trigonometry, SOHCAHTOA. As soon as I have a right triangle, I can apply Pythagorean Theorem, a squared plus b squared equals c squared. Okay? And we're going to see some of these things pop up as soon as we get into measurements. Okay? But all of that stuff comes with finding relationships between angles and side lengths. Okay? So I'll come back to that in just a minute. All right? So let's talk about the punchline of this entire section. It's this. Here is the area of a regular polygon formula. And this is important because unlike, say, an area of a triangle or the area of a quadrilateral where they each seem to have their own unique sets of formulas, it would be a real pain if I had to have a completely different formula based on the number of sides of a figure. So there would be a completely different formula for a pentagon than there would be for a heptagon, for a dodecagon. That it would be a real pain if every single new shape had its own formula. This boils it down to one formula, regardless of the regular polygon I'm dealing with. Again, the key operative word here being regular, so all this other baggage comes along with it. But any regular polygon, I can use one of these formulas. And for the record, this is the same formula. The only difference you may notice here is this capital P representing perimeter of the given polygon I'm finding the area of, compared to n times s, where n is the number of sides of a given polygon, s being the side length. Because it's a regular polygon, it's equilateral, so finding the number of sides. So if I had like a 7-sided heptagon, and I knew one of the side lengths, s, just multiplying it by 7 gives me the perimeter, capital P, of that. So these are the same formula. It's just either breaking it down one way or the other. For the record, we're going to use this guy most of all because it's kind of like a rare case where they're going to explicitly tell you what capital P perimeter is. So this will be the one that's kind of like our default equation right here. So let me break down what we're looking at. Capital A area of some regular polygon, whether it's a quadrilateral or a hexagon or an octagon or whatever, is going to equal the following. 1/2 times lowercase a being the apothem measurement, the distance from the center to one of the sides, times n being the number of sides in the figure, which will either be shown to us in a diagram where we're just counting sides, or they just tell us a name and we translate that name into the number of sides. And then s being the side length of one of those sides. Okay, so translating this from this hexagon diagram right here, apothem A in this diagram would be the distance from P to Q. So if I can find the distance of PQ, or I'm given the distance of P to Q, that would be the lowercase a apothem length. N in this figure would be the number of sides. This is a 6-sided hexagon, so n would just be 6 in that case. And then s would be one of the side lengths, so m to n at the top right here would be one of the 6 side lengths. If I could find that length, then I have everything I need to find the area of that hexagon. For the pentagon, apothem lowercase a would be from F to G, the perpendicular distance there. N in that case would be a 5-sided pentagon, so n would be 5. S for a side length would be the distance of one of the sides, so A to B right here would be a distance of one of the sides. So that's kind of the introduction into what we're going to be dealing with. Those apothem and S side lengths can be a little tricky to solve for. So in the next clip, I'm going to kind of break down what you're going to see in your assignment and then work through one of the examples. And then in another clip, I'll do one more repetition of it just so you can kind of see it worked out and how it can be solved for that. But I'll go ahead and conclude this clip. I'll go ahead and stop the recording right there.